So we're back to more aspects of aqueous equilibrium. We're going to skip over the acid-base titrations for just a brief moment, and we're going to focus in this discussion on solubility equilibrium and factors that affect the solubility of substances in water. Solubility equilibrium is really just looking at the solubility product for dissolving something. So this is a physical process, and if we do the K equilibrium for this, if we leave out the solid, we get that the K is equal to the concentration of the silver ion times the concentration of the bromide ion, and we give this a special name, as the title is called, the KSP, or the solubility product for this reaction. Now, we're going to invoke another convention here. We're going to use S, and we're going to define that as the solubility of AgBr in terms of moles per liter. All right, so this represents the number of moles of silver bromide that will dissolve per liter of solution. Well, what that means then is that our equilibrium expression over here can be rewritten as, because for every 1 mole of silver bromide that dissolves, we have 1 mole of silver ion and 1 mole of bromide ion. So that solubility is also going to be equal to the concentration of the silver and the concentration of the bromide. So our KSP ends up being equal to the solubility of the silver bromide squared. So we'll make use of that in the next problem here. We're told that we have the molarity of a saturated solution of silver bromide is 7.07 times 10 to the minus 7th. Now again, this value is not the KSP, that's the solubility. So that's what S is equal to. So we want to find out the value of the equilibrium constant. So it's simply a matter of plugging that into our formula. And so we'd have the KSP is equal to S squared. So it would be 7.07 times 10 to the minus 7th. Quantity squared, which would give us then a KSP value of 5.0 times 10 to the minus 13th for our KSP value. So again, it's really just a simple matter of, if we know the molarity of the saturated solution, and again, solubility means, what is the maximum that we can get dissolved. So the solubility of the silver bromide is 7.07 times 10 to the minus 7th. We just plug that into our expression as the concentrations of the silver ion and the bromide ion, and we can get the KSP value. Now in this one, we're going to, a little bit more complicated. Here we're given the KSP value, and we have an added kind of dilemma here that we're not forming 1 mole of each ion. We're actually forming, for every mole of the lead 2 iodide that dissolves, we actually form 2 moles of iodide ion in solution. So our formula will be a little bit different here. Still the same expression. So our KSP would be equal to the concentration of the, excuse me. Damn. Oh, sorry about that. So the KSP will be equal to the concentration of the Pb2 plus times the concentration of the I minus squared. So again, we shouldn't have any problem writing that. Now, if we think about the solubility, remember the solubility is defined as, or S is defined as the solubility of the PbI2. Well, for the lead part, that's going to be pretty simple. The lead for every mole of PbI2 that dissolves, we have 1 mole of lead that dissolves. So that concentration will be S. For the iodide, for every mole of lead 2 iodide that dissolves, we actually get 2 moles of the iodide. So we're going to put down a 2S for the concentration of the iodide, but then we need to remember to square that. So it's 2S squared. So what we end up with then is if we factor that exponent through, we're going to end up with S times 4S squared, or 4S cubed, being equal to our KSP. And our KSP is given to us up there, 7.1 times 10 to the -9th. And so now it's a matter of getting our calculator out and plugging the correct numbers into our calculator. And if we do that, we end up with a value of S equal to 1.20 times 10 to the -3rd. And that would be the molarity. So there's the molarity of our PbI2, the moles per liter that dissolved. And obviously, if we look back at our solution, that would be the concentration of lead ion, and the concentration of the iodide ion would be 2 times that amount. One more quick mathematical example. Here we are trying to find the KSP, and we're given the pH of the solution. So again, we'll write down our KSP expression. KSP equals the concentration of magnesium times the concentration of the hydroxide ion squared. So we can invoke the, using S up here if we wanted to. It might be easier just to kind of use the hydroxide ion concentration and compare that with the magnesium concentration. We know that the pH is 10 to the 13th, which means the pOH, if we subtract that from 14, the pOH is going to be equal to 1, which tells us that the OH minus concentration here is going to be equal to 10 to the -1, or 0.10 molar. All right, well, if we look back over our expression here, it's pretty easy to see that if the hydroxide ion concentration is 0.1, the magnesium ion concentration is going to be 1/2 of that. And again, you could do the same rationale if you figured out, where S is the concentration of the magnesium ion, hydroxide is 2S. If we know the hydroxide, the magnesium ion is 1/2 of that. So we can go ahead and just plug our values in here. So we'd have 0.050 molar for our magnesium ion concentration. Our hydroxide ion concentration is 0.10. Have to remember to square that value. Molar. And if we plug into our value here, we get a value of 5 times 10 to the -4th for the KSP for the magnesium hydroxide. The factors that affect solubility, so now we'll look at this kind of a qualitative standpoint. The factors that affect it, of course, are temperature. Now, you want to keep in mind that really when we talk about factors affecting solubility, we're really looking at Le Chatelier's principle. So if you go back to our chapter on equilibrium, Le Chatelier's principle is going to determine whether it shifts to the right and more of it dissolves, or it shifts to the left, which means less of it will dissolve. So number 1 on the list is temperature. Obviously, that affects equilibrium constants. If you increase the temperature, by and large, for solid substances dissolved in water, you're going to increase the solubility. For the second one, common ion effect, so this is the, again, the Le Chatelier's principle. If you increase the concentration of one of the reactants or products, it's going to shift the equilibrium in the other direction. So if we try to dissolve silver bromide in solution, but we've already got bromide ion present there, or we've got a saturated solution, we add more bromide ion, that's going to shift the equilibrium back over to the other side. So it's pretty easy to understand how common ions affect these things. pH is a little bit harder to understand, but pH will affect, again, the amount of ions that happen to be dissolved. So we'll take a look at that in just a moment, as well as the formation of complex ions. So the formation of complex ions will tend to remove some of those ions from solution. If you remove some of those ions from solution, that's going to shift the equilibrium to the right, and you would actually get more of your solute, more of that solid to dissolve, and increase in solubility. So here we have a solubility and pH scenario. From a simple standpoint, here we have a precipitate of, or a saturated solution of magnesium hydroxide. So we have some hydroxide ions dissolved, some magnesium ions dissolved, but the bulk of it's going to be magnesium hydroxide in solid form. If, however, we add hydrogen ion to this, obviously that hydrogen ion is going to be capable of reacting with the hydroxide ion, forming water, thus reducing the amount of hydroxide ion in solution, which would then shift the equilibrium so more of the magnesium hydroxide would dissolve. And so you can see that if we keep adding more acid, we keep reacting with the hydroxide, and it keeps shifting over, so more and more of the magnesium hydroxide will dissolve, until eventually, if we added enough acid, we would have all magnesium ion in solution and none of the magnesium hydroxide solid. Another kind of practical application of that is the formation of sinkholes. If you look at the diagrams here, they give kind of a, there's obviously a large picture of a huge sinkhole that occurred. And then the picture above kind of gives you an explanation as to how that happens. In the diagrams, diagram A, you see that there's this hole down in the porous limestone. So this is a confined aquifer. So there's water that runs through there. And limestone, let's see if I can write this over here. Limestone is calcium carbonate. And the dissolving of this, calcium 2 plus CO3 2 minus. And the KSP for this is actually fairly small, 4.5 times 10 to the minus 9th. So it doesn't dissolve to any great extent in water. However, if you have acidified water, what happens is that H plus in the acidified water will react with the carbonate, forming HCO3 minus, so the bicarbonate ion. And basically what we're doing is we're going to reduce the concentration of the carbonate ion from the addition of the acid here, which will then shift this equilibrium to the right. And so as more and more of that limestone dissolves, you create these holes. And what happens is the water runs through there, the ions then get flushed away, and it holds up until at some point the force of gravity will break through the clay layer, and you get what's seen here as a sinkhole. And lastly, the formation of complex ions. If you take a solution of aluminum hydroxide or of aluminum and you add it to water, you get a complex, or you get a precipitate of aluminum hydroxide. So it's in that middle picture here. Now, if you add more hydroxide ion to this, what ends up happening is you form a complex, and I don't know if you can see it down here, but you add one more hydroxide onto that, and it becomes actually soluble. So that precipitate actually will disappear because of the formation of that complex ion. Now, you can also cause the precipitate to disappear by adding acid to this. Obviously, that would use up the hydroxide, similar to the magnesium hydroxide. So you can go this way by the addition of acid, or you can go this way by the addition of hydroxide. But either way, you can actually, cause that precipitate to dissolve. And so we'll show you an example of this in class, because they're pretty interesting, the formation of those complex ions. So that's it for the solubility for now. And we'll do a couple problems on these to make sure you can do the quantitative part of this.